If you like this video, please press the subscribe button to subscribe to this channel, and also give it a thumbs up. You can also support this channel with a donation by using the link in the description. A key point of general relativity is how gravity works. Newton based his model of gravity on the physics he knew and considered it to be an attractive force. General relativity shows gravity to be a result of a curvature of space-time. The connection between gravity and mass has been known since Newton's time. General relativity by itself, however, does not say why mass bends space-time. Now we can make the connection between mass and the curvature of space. Here is the Schwarzschild metric and its corresponding metric tensor. They show how space-time curves within a gravitational field. It also predicted the existence of black holes. Here are the formulas showing gravitational time dilation and gravitational length contraction relative to an object at a distance. It shows abundantly clear that time is slower inside a gravitational field and length is shorter when compared to an object outside. The velocity of an object falling from infinity in a gravitational field is defined by the first formula. The second formula results when you square this velocity and divide it by the square of the speed of light. Furthermore, when we take the formula for centrifugal force, which in the case of an orbiting body is orbital velocity squared divided by r, and substitute in the formula for orbital velocity, we get Newton's formula for gravitational acceleration. Here is a common depiction of the warping of space in general relativity. There are, however, several problems with this. First of all, the grid is two-dimensional, not three-dimensional. But also, the Earth is still three-dimensional. To make it a more consistent illustration, the Earth would have to also be two-dimensional. Here is another common type of illustration of the curvature of space-time in general relativity. There are, however, several problems with it. The first is the direction in which it faces. Since in most space-time diagrams, the future is depicted upward. Meanwhile, in these diagrams, the curvature of space-time is depicted downward. This should be a more consistent illustration with most space-time diagrams. Now, admittedly, it is essentially arbitrary, but this does provide a better illustration. Furthermore, these illustrations also have a far greater curvature than would be the case in reality. In reality, the curvature of space-time would result in a tilting of both space and time that would be equivalent to what you would get for the escape velocity at that point within special relativity. In this illustration, the upper arrows represent the arrow of time at various velocities, and the bottom one represents the equivalent tilting of space. In this illustration, it shows that when the escape velocity reaches the speed of light, which is the event horizon, the tilting of both are only 45 degrees, not what is often depicted in diagrams, which often reaches 90 degrees. Here is an illustration of the tilting of space-time at various distances. When connected, they form an approximate curve similar to what you would expect in general relativity. This illustration shows how time is tilted at various distances. When you combine the two, you get the tilting for both space and time of the escape velocity under special relativity. When you connect the spatial lines, you get a good view of the curvature of space-time under general relativity while showing how it produces gravity. This shows the effect of the tilting of time. It literally moves space towards the gravitating body. One of the consequences of this is that the surface of a planet or any other object is actually accelerating outward. This is how the curving of space-time produces gravity under general relativity. Now, the object described above would probably be a neutron star. The escape velocity would be a whopping 0.222 c, or 22.2% the speed of light. This shows that the actual degree of curvature is not as much as is often depicted. It is evident that the mass drags the space-time coordinate system with it as it moves through time. This has the effect of bending both space and time at a given point in the same manner that relative velocity does. Consequently, you have an acceleration that is caused by it bending space-time and not a force being applied to the object. This shows how the mass of an object bends space-time, causing gravity. So ultimately, it is the motion of a mass through time that causes gravity. This is because it is this motion that bends space-time. In conclusion, according to general relativity, gravity results from space-time curving to produce the same tilting between space and time that results from any other relative velocity. The effect results from the motion of a mass through time. This effect extends naturally from our model. Here are some upcoming topics: unifying natural and supernatural, fine-tuning this theory, and predictions from this theory.